the definite integral. Up until this point, we've been approximating the area under the curve by drawing in little rectangles, which provided us with an overestimate and an underestimate. We also determined how we could write the sum of all these rectangles in an efficient way, which was called the Riemann sum. So as a reminder, the left-hand side Riemann sum is the sum seen here that goes from 0 to n minus 1 of delta t f of t sub I. The right-hand Riemann sum looks exactly the same, except that our index bounds go from 1 to n. So that's how we determined that we could succinctly write a generalized function for area under the curve for a left-hand estimate and a right-hand estimate. Now, remember when we were doing our problems using estimates of rectangles, we determined that if delta t could get smaller and n would get bigger, then that would make a better estimate. Again, the idea is that the more rectangles we can put under the curve, the better our approximation is going to be. We want to put in so many rectangles that they are essentially lines that go directly up until they hit the curve, therefore not having any extra area and not missing any area, and therefore giving us the exact area under the curve. So mathematically, if we want to put in almost infinitely amount of rectangles here, the way that we're going to represent that is with a limit. So we're going to take the limit as n goes to infinity of our left-hand approximation and the limit as n goes to infinity of our right-hand approximation. And when these are equal, that means that the overestimate has come down and the underestimate has come up. And so our bounds are equal. And when that happens, we have the exact area under the curve. So if we put in enough of these rectangles, we're able to determine the exact area under a curved function. So when that happens, we have something that we call the definite integral. So here, the definite integral looks like this, and it comes from sort of stretching out this summation notation. So this is called the integral, and it's called a definite integral because it's calculating the area under a curve between 2 points. So notice that the points on the integral symbol are a and b. We talked about how a was our starting point and b was our ending point. That translates directly here. Now, f of x is the function that we are looking under. Dx has become an operator, and the operator tells us what the variable is here. So this says, find the area under f of x between a and b exactly. So that means that we are assuming that n is going to infinity, that these little rectangles are summing up exactly, and we're going to spit out the exact area under the curve. So how does this work? Let's look at some examples. Earlier in this chapter, we looked at the problem that said if t is in hours of a 20-hour period, the rate at which bacteria population is growing is given by f of t equals 3 plus 0.1 t squared. We then approximated the change in bacteria under the curve using delta t equals 4. So we set up a table and we plugged our numbers into our rate, and we were able to use left and right hand estimates. And when we did, our best estimate was 312 bacteria. So now that we know that the integral represents the exact change under the curve, we can find the total change of this bacteria on this period by using a computer or calculator in order to determine the exact area under the curve. We needed to know the right syntax, which we didn't have until this point. When we do this exactly, we get 307 bacteria. That's pretty close to what our estimate was when delta t equals 4, but now we know the exact answer. So let's look at some examples, and I want you to practice plugging in these functions into your calculator and using the integral context in order to calculate the following things. Example 1. Use your calculator to compute the area under f of x equals x squared plus 3x plus 1 between 0 and 3. You can see on my calculator on the left the syntax that I use on my TI-84 to compute this area. Now, depending on your calculator, you should be able to look up in your manual how you calculate integrals and areas under curves so that you can also do this on your calculator. So when I plug in all my function and my bounds, 0 to 3, I get 25.5. So that means that the area under the curve between 0 and 3 is 25.5. On the right is a picture of what that looks like. So I've graphed the function and I've shaded in the area between 0 and 3. So the area between the function and the x-axis is going to be 25.5, which I can get computing on my calculator. However, even though we now have the tools to be able to compute this exactly on our calculator, sometimes we ask questions using the integral where we still need to do some estimating. So let's see how those types of questions are worded.